Okay, good morning. Today we will cover the rest of chapter 3, finish it up, a little bit of the theory of the capacitors, example problems, and then Friday we'll begin chapter 4. Okay, so let's begin where we left off. We talked about charging of the capacitor in the previous class, where we connect a voltage source to a capacitor, the charge imbalance, electrons flow through the circuit, charge accumulates on both sides of the parallel plates, which we can read and measure as the capacitor voltage. If you take this charged capacitor and you remove it from the circuit, if it's an ideal capacitor, it will hold its charge indefinitely, right? It will hold its charge indefinitely. But real life capacitors are not made of ideal materials. Real life capacitors will have an insulating material that has very high resistance, but it will still allow for a slow discharge. Meaning, if I have a fully charged capacitor, and I'm going to enlarge the diagram. You have charges on both sides of the capacitor. You remove it from the circuit. An ideal capacitor will hold this charge like a battery infinitely. But a real life capacitor, this is the insulator, insulating material, will actually discharge through that insulating material. Okay, and we can electrically model this as a resistor in parallel with that capacitor. Okay, so the stored energy of the capacitor would discharge through those terminals. So similar to an inductor, where inductor we model as a resistor in series, we model the capacitor with a resistor in parallel. That allows us to explain how and why a capacitor would discharge through itself, even though it's not connected to anything. Okay. Now, of course, the amount of time it takes for the discharge will depend on the size of the capacitor. It will also depend on the amount of voltage or energy that is stored in the capacitor. So going off on a little bit of tangent, if you take a charged capacitor out of the circuit and you short the two terminals together, what will happen? A charged capacitor is like a battery. What is the resistance of a short circuit wire? 0 ohms. If R is 0, what is I? I is infinity, right? So when you short the terminals of a capacitor, it's like shorting the terminals of a battery. All of the energy that is stored in there is now being discharged through that short circuit wire. But because that the R is equal to 0, I goes to infinity, all of it is discharged almost instantaneously. Capacitor, compared to a battery, has very small energy storage. That energy is released. Capacitors are small, so you'll see a small spark. Big capacitor with larger storage, you might see a bigger spark. A huge amount of storage, you might even see an explosion. And that's the reason why they always advise you, right? They say, if you have batteries, do not store them with any metallic objects. So you don't want to inadvertently short out the two ends of your batteries. Otherwise, you have the Galaxy Note 7. You don't remember that a few years ago? What happened there was someone or a team was designing the batteries of this phone, and in the pursuit of thinner and thinner devices, they made the walls between the cells very thin. That led to a short circuit between the positive and the negative terminals of the cells. And so because it's a short circuit, I is 0. Not I is 0. R is 0. I is infinite. That energy is now being released. It's overheating. Obviously, when electrical energy is dissipated, it's dissipated in the form of heat, thermal energy. So it got hot. But it's not a capacitor, meaning the stored energy does not A battery has much more stored energy than a capacitor. And so the battery energy is still being released. It's being released. It's being released. It's being released for a long period of time. Heat is being built up with nowhere else to go, and it resulted in an explosion. That's what happens. That's also one of the reasons why manufacturers will tell you not to use a non-approved charger with their devices. Well, that's the excuse they use. They also want to make money by selling you expensive chargers. But initially, when chargers first came out, like generic off-brand chargers, the designs were poor. And so if the design is poor, every charger will supply, it's like a pipe. It just sends in a huge amount of energy. The device will have an auto shut-off. So if it's a smartphone, a laptop, or whatever device you are charging, will have a shut-off signal. It'll tell the charging device, hey, I'm full. Do not send any more energy. Shut it down. But poorly designed chargers do not receive, they will receive the signal, but they won't do anything about it. They'll keep sending the energy. And so the energy is being sent continuously into the battery, even though it's full. So the battery now swells up. And when it swells up, after a certain point, it's going to explode. So that's why manufacturers use that as an excuse, saying don't use non-approved chargers, otherwise your devices might explode. A real life analogy is if you've ever filled up gas in your cars or your vehicles, there's an auto shut-off vapor evaporation system inside your gas tank that sends a signal to the gas pump or the fuel pump that I'm full, stop. And that is also the reason, again, this general knowledge tangent away from the class material. They'll tell you do not top off. The reason is when you top it off, there's a carbon filter or absorber in there that gets clogged up. If that gets clogged up, it won't function anymore. That's the reason they tell you not to top off. Anyway, coming back to our topic under consideration, capacitor stored energy is finite. So you short circuit the lead, you might see a small spark. If you do this to a battery has much more stored energy than a capacitor. It'll lead to an explosion. So it's always safer to use a resistor to discharge a stored capacitor. Okay. Capacitance is the amount of energy that is stored or amount of charge that is stored. You apply a voltage of 1 volt. If it stores a charge of 1 coulomb, you are now we say that the capacity of that capacitance is 1 coulombs per volt. The unit is named after who? Michael Faraday. Absolutely. So 1 farad is the amount of capacitance that can store 1 charge for every 1 volt applied. C is Q over V. That gives us Q equals CV. This is the equation we'll use to derive, well, not derive, but like one-step derivation to write out the current equation, IV equation. Okay. And there are some quick, small examples I like to use just to point out how we can actually change the voltage and change the amount of capacitance that is required. So, example A, and you don't have to write anything down. This is just conceptual. Okay. Example A, we have an applied voltage of 2 volts. We are storing 6 coulombs of charge. So the measured capacitance required would be 3 farads. Okay, 3 farads of capacitance can store 6 coulombs of charge if you apply 2 volts. Example B, we apply the same 2 volts, but now the capacitor design is 6 farads. When I say capacitor design, physical construction is a big factor in capacitor value. Okay. So again, capacitor designed to hold 6 farads. And so the stored charge can now go up to 12 coulombs, twice as much as example A. All right. Same amount of voltage being applied, but capacity is now higher. And then if you look at example C compared to A and B, Same amount of charge, 12 coulombs, but now physical construction of the capacitor requires 8 volts, not requires 8 volts, can take up to 8 volts. So higher amount of voltage being applied. And if your materials can withstand that high amount of voltage, then the capacitance value is very small, 1.5. Okay, 1.5. And that is the reason they designed electrolytic capacitors, because they are very, very thin. The separation between the two plates is the smallest of all capacitors. Okay, it's a gel-like formation that is just coated on it. And so it is far thinner than anything we can actually make. Speaking of which, physical construction of a capacitor is given by the expression epsilon A over D. Distance D is between the two plates. The farther apart, the smaller is the capacitor. The closer the two plates are, the larger the value of the capacitance, inversely proportional. So D is right here. A is the cross-sectional area of the plates, and the equation is C equals epsilon A over D. Epsilon is the permittivity, and the product of epsilon 0 times epsilon R. This is epsilon 0. Constant 8.85 and 10 raised to minus 12. Very similar expression to the one we saw for the inductor. Inductor, it was mu, the permeability. Mu is mu 0 times mu R. Absolute permittivity times relative permittivity, permeability. And here it is epsilon 0 times epsilon R. Epsilon 0 is a constant. Epsilon R is the material property of the insulator. Material property of the insulator. Okay. So epsilon 0 times epsilon R times A over D. So larger the cross-sectional area, the larger the capacitance. The smaller the distance between the plates, the larger the capacitance. So now that begs the question, what exactly is A? Here it states it's the area of either plate in meters square. But that's based on an assumption that both plates are exactly the same size. But what if the plates are not of the same size? Then what is A? Yes. That's the answer I received for the previous two sections. The answer is correct, but not entirely complete. And in this case, a picture is worth 1,000 words. It's the overlapping. So as soon as I drew out the picture, everybody understood what's going on, or at least most of you did, right? Definition of a capacitor. Two parallel conducting plates. If it's one plate, there's no capacitor. So as you see in that image, the only area where you have two plates is the overlap. So in that case, the cross-sectional area depends on the dimensions of the overlap, not on anything else. Yes. Yeah, the construction, yes. But it's impossible to fabricate exactly the same distance between the two. There's always going to be minor variation. The smaller that you go in dimensions, the more that difference will matter. Yes. So the question being asked is, does charge move normal to the plate? Essentially, yes. But honestly, I would say I haven't delved too much into the physics of charge movement. So I would not be able to give you that definite answer. But that's a very good question. Now we're talking about transport phenomena. Okay, so then let's go into the equations and then the example problems. So we established that Q is C times V, product of the voltage and the capacitor, right? Q is equal to C times V. If you take the derivative, dQ over dt, and on the other side, we get C dV over dt. dQ over dt is the rate of flow of charge, which is nothing but current I. So we have the IV equation. I is C dV over dt. Exactly the same structure as the inductor equation. For the inductor, the voltage and current were flipped. We had inductor voltage V equals L di over dt. Here it's IC dV over dt. And then if you wish to find the capacitor current, if you're given the voltage, you simply integrate both sides. And so capacitor voltage, oh, not here, not this slide. Capacitor voltage would simply be integral of the current. That's it. Don't worry about the derivation and the limits of the integration. I will explain all of that when we get to the example problems. Okay. So again, capacitor voltage, capacitor current, I is C dV over dt, derivative of the voltage. Capacitor voltage is integral of the current. Power equations are still the same. Power is the product of voltage and current. Notation, this I do on purpose. Remember, for the inductor, I simply wrote out P equals VI. But I stated, right, you can have a subscript perhaps, maybe, maybe not, I or IC or I of t as a function of time, or IC of t. They all mean the same. They all mean the same, okay? So previously I used to just keep it without any subscript, without any, functions of time. And then I would tell the students, but then because they hadn't seen it before, if they encountered something like that, they would say, this is different. We've never seen this before. So I make it a point to show that this is exactly the same thing, okay? The same equation could simply be P of t is V of t times I of t, or P equals VI. That's all. They all mean exactly the same thing. Energy is half CV square. For the inductor, it was half Li square. Again, energy is simply half CV square. Half CV square. Okay. All right. 4 examples. All of the examples use a capacitor. First 2 examples, we are given the capacitor voltage. We are asked to find the current. Then we are given the current. We are asked to find the voltage. Examples 3 and 4 are exactly the same. Same in the sense. In the first example 3, we are given the voltage. We're asked to find the current. Example 4, we are given the voltage. We are given the current. We're asked to find the voltage. All of these examples can apply equally to an inductor and a capacitor. If the quantities are flipped, meaning if you're given the voltage, you use you integrate the voltage to find the excuse me. For an inductor, if you're given the current, you take the derivative to find the voltage. And if you're given the voltage, you integrate it to find the inductor current. So all examples apply equally to capacitors and inductors. And once we solve the first one, I'll point out how the same example can be used for an inductor also. At this point, these examples are less about circuit analysis and more about just math. Okay, actually, it's very little of circuit analysis in here, and it's just math. So if you take example 1, for instance, example 1, we are given the value of the capacitor, 5 microfarads. We are given the value of the voltage. Doesn't matter what value it's given to us, but we know the equation. Capacitor current I, we are asked to find I. I is C dV over dt, product of the capacitance and the derivative of that voltage. So it's just math. Okay. Capacitor current I is simply the product of C and derivative of the voltage, dV over dt. Plug in the value and solve. See if your answer matches up with mine. 5 into 10 raised to minus 6. D by dt of 10 cos 6000 t. What is the derivative of cos x? Minus sin x, right? Sin x is cos x is minus sin x. How about cos of ax? Minus a sin ax, right? So you take it outside, solve it, and you'll have your answer. So here, 5 into 10 raised to minus 6. There's a minus. We'll take it all the way outside right here. And then what do we have? 6,000 comes outside. And then we simply have 10 sine 6,000 t. You solve this and you obtain minus. Anyone solve it yet? Anyone online solve this? Minus 0.3. 6,000 t and amps. If you solve this, does your answer match up? Again, there's nothing about circuit analysis in here except the equation, right? So I always say, don't have to memorize the equations as long as you're able to understand it, recognize it, and know how to apply it. In this case, we are given capacitor, they're given the voltage, we are asked to find the current. We should recognize the problem statement and realize the equation we need is I is equal to C dV over dt. Plug in the values and you solve. Make sense? Any questions? Okay. The same example problem for an inductor would look like this. Now, I'm not going to solve this, but just to illustrate. Let's say inductor value L is given 5 millihenry, perhaps. And then you're given the inductor current I of t as 10 cos 6,000 t amps. And you're asked to find the voltage. Well, if you're given L, you're given I, plug in the equation, V is L di over dt, and solve. So again, the example problems, all 4 example problems work equally for capacitor as well as an inductor. It would be your job as an engineer to look at the problem statement, understand it, and determine which equations and which method to use. All right, any questions before I move on to example 2? Okay, example 2, we are given the current and we are asked to find the voltage for the capacitor. This time we integrate. First, we perform the derivation, now integration. So, capacitor voltage would be 1 over C integral of the current I of t. We are not given the limits of the integration. We are not given anything else except the value of I of t. So if that's the case, we simply choose the limit of the integral as 0 and t. 0 is when we begin our analysis. The end point is simply the variable t because we want to obtain the answer also as a function of time. Okay, so we'll integrate between 0 and t. You plug the values in. V is 1 over 2 into 10 raised to minus 6, 0 to t, 6 times e raised to minus 3000 t into 10 raised to minus 3. You have to pay attention to the units. It's milliamps. So you have to take that into account. Milliamps. All right, we solve this, right? So what do we have? We have 6 constant minus 3000. That comes outside. So minus 3000 over 2 raised to 10 raised to minus 6. 10 raised to minus 3 also comes outside. That gives us 3000 over 3000. And then integral of minus 3000 t. The variable is also t and the limit is also t. Okay, we want the final answer as a function of time. And so again, should be 2 different things, but same variable. Plug in the values. You get minus 3000 t minus e raised to 0. And so we obtain 1 minus e raised to minus 3000 t volts. As I was saying, far less about circuit analysis, more about just math. Okay, how much time left? It's about 20 minutes left. So I want to finish up examples 3 and 4 in those 20 minutes. Right. Okay. So now we come to a technique known as piecewise linear analysis. In this case, there is no mathematical description or analytical description of the voltage. The voltage is given to us in the graphical form, okay, a chart. The graph describes the voltage that is applied to a capacitor between 0 and 8 milliseconds. Time is always on the x-axis. Quantity can be voltage, can be power, can be current. In this case, it's voltage. So voltage as a function of time is given to us. However, before we do anything, we need an equation to describe this function. We call, in electrical engineering, we call this a function. So we need an equation to describe this function. This function is the voltage as a function of time. So what we do is we use this technique to divide up the graphical chart or graphical description into individual pieces. And each piece will then have a linear relationship with time. And hence this technique is also known as piecewise linear analysis. Okay, piecewise linear analysis. Each piece is linear with respect to time. And here, quite easily we can see, we can divide it up into two parts between 0 and 6 and 6 and 8. I'll call that T1 and T2. Now, here's the beauty of this technique, especially for this kind of problem. I will use the slope line intercept method to describe the slope of that, to describe that line, right? It's a straight line. So we can use the expression y equals mx plus b. Now, you may be familiar with this equation, perhaps with different variables, right? B, of course, is the y-intercept. Y is voltage V, X is T. What is M? What is M in the slope? M is the slope of the line. But in this case, the line is describing voltage as a function of time. So if you take the slope, what do you get? Slope describes the difference of the x-axis, the difference of the y-axis. So you get dV over dt. dV over dt. What is our capacitor current equation? I is C dV over dt. So this is simply C times M. You don't even have to, we don't even have to describe the line at all. We simply find the slope multiplied with the capacitance. That gives us the value of the current. It's as simple as that. Slope, of course, as I just said, is the difference in two coordinates. So for T1, between 0 and 6, the slope M1 can be written as, I'm going to take the two endpoints of the line. That's what I usually do. So 24 minus 0 and 6 minus 0 milliseconds. That gives me a value of what? 4,000. 4,000 volts per second or 4 volts per millisecond. Either is right. And so my current I1 is C times M1. Current capacitor is given as 5 microfarads, 5 into 10 raised to minus 6 into 4,000. And therefore I1 has a value of 20 milliamps. There is no t in there. It's not a function of time. It's constant with respect to time. You can go ahead and solve for the second portion. Determine the slope, multiply with the capacitance, see what answer you get. Take the two endpoints. The two endpoints would be right here. Coordinates would be 6 and 24. And then for the last one, it would be 8 and 0. So for T2, M2 would be 0 minus 24 volts. X2 would be 8 minus 6 milliseconds. That gives me minus 12,000 volts per second, or minus 12 volts per millisecond. Therefore, current I2 is C times M2 minus 60 milliamps. You plot this, and you get what is shown in the second image. Straight line of 20 and a straight line at 60 or minus 60. All right, think over it. Let me know if you have any questions. Any questions at all? And again, the procedure can apply equally to a inductor, except the quantities, voltage and current would be flipped. Okay. All right. 13 minutes left to finish up example 4 in that time. Same approach, piecewise linear analysis, but this time we are given the current, and now we're asked to find the voltage. Instead of performing just a simple derivation, we now have to do an integration. And I will explain math, of course. I would assume your engineering students probably know your math better than I do. But I will explain how we find the, how we define the limits of the integration, and then the stored energy that we have to take into account. Okay, the initial stored energy. So the two time periods here are between 0 and 2, and then 2 to 4. Okay. In simplicity's sake, I'm going to point this out. This top point is 16 microamps, and the bottom one is minus 8. Okay, minus 8. All right, so T1 is between 0 and 2 milliseconds. Slope M1 for T1, slope M1 can be written as 16 minus 0 microamps, 10 raised to minus 6, and 2 minus 0 milliseconds. So M1 can be written as 8 into 10 raised to minus 3 amps per second, or 8,000 amps per millisecond. No, sorry, 8 amps per millisecond. Okay, then this time I do need the expression for the current I, right? Because I need to integrate, I do need the expression, so I will plug the value in and find the expression. Y is current, M is 8, and then x is t, y-intercept is 0. So my I of t for the first time period is 8 into 10 raised to minus 3 t, 0.008 t amps. This is the mathematical expression that I would need to integrate. Okay. For T2, I don't need to bother with anything. It's a constant value, minus 8. Okay, constant value, minus 8 microamps. So again, the purpose is that to express the graphical description as a mathematical expression. So then we can perform mathematical analysis and calculations on it. Okay, that is the purpose of going through this procedure. So now that we have our equation, we'll go ahead and perform our integration. First time period goes from 0 to 2 milliseconds. That's the only, that's the limit of our integration. But we want the answer as a function of time, right? It's going between 0 and 2 milliseconds. It could take any value. Time could take any value. It could be 0.1 milliseconds, 0.005 milliseconds. We need an expression that would allow us to find the value of that voltage at any given point in time between 0 and 2 milliseconds. Does that make sense? So our final expression should be a function of time. So my initial period, initial analysis will begin at 0 milliseconds, but the end of my integration, the end limit would still be the variable t. Okay, the variable under integration is also t, and the end limit is also t. Two different things, but the same variable. Make sense? Hopefully, yes. So for time period t1, we are integrating between t0 and t. T0 has a value of 0 milliseconds, and the end is also t. Begin and end. Okay, the limits of the integral are 0 and t. So we plug that value in. What do we have? We have voltage V is, of course, 1 over C integral T0 to T of I. And oftentimes in some books, in some authors, some instructors, we change the value of the variable from T, we change it to X, but that change is simply to avoid confusion. In either case, it does cause a little bit of confusion if things are not explained properly. So again, whether it's T or X or Y or A or B, it does not matter. It's you're simply using it as a placeholder variable to actually perform your calculation. That's all you're doing. That's all we are doing here. So plug in the values. C is 4 microfarads. And then value of I, 8 into 10 raised to minus 3 T. We'll bring the constant outside. 8 into 10 raised to minus 3 divided by 4 microfarads. And then integrate x. So we get x squared over 2. The limit is 0 to t. And you plug in, and you obtain an expression 10 cube times t squared volts. 10 cube times t squared volts. Final answer is as a function of time. In this expression, you could put in any value between 0 and 2 milliseconds, and it'll give you the value of the voltage at any given point in that time interval. So this expression is valid only between 0 and 2. Does everyone understand that? Okay, how much time left? 5 minutes left. Let's go over to the second one. Now, at the beginning here, we are summing up, right? We are summing up the voltage across that capacitor between 0 and 2. But what if there was some initial voltage present in the capacitor between time t equals 0? That would be described by the initial stored energy, and we would have to add that on to our integration. Okay. Between 0 and 2, we integrated, meaning we summed up everything, we found the voltage. But before or prior to time t equal to 0, there was no stored energy. If it's not mentioned, then you take it as 0. If it is 0, then we don't have to add it. However, when we get to the second time period, meaning T2, in T2, the value of T0, the beginning of my analysis, is 2 milliseconds, not 0. I'm analyzing between 2 and 4 milliseconds, right? My end period will still be T because I want the final answer as a function of time. So I will set the limits of the integration from 2 milliseconds to end at T. But the initial stored energy for the second period is the ending energy, or the energy present in that capacitor at the end of the first time period. The first time period ended at 2 milliseconds. So stored energy at t equals 2 milliseconds is the initial energy for the following analysis period. Okay. So in the following analysis period, voltage at time t equal to 0, or T0 is voltage at t equals 2 milliseconds, which we obtained from the previous page as 4 millivolts. You simply plug in the value of t equals 2 milliseconds into that expression we determined previously, and you find the value of the voltage as 4 millivolts. We have to add 4 millivolts to the next step. You can see that here. 4 millivolts added in the next equation. So I only have 2 minutes left, so I'm going to go through this quickly. Let's see. Before this is going to go fast because we have a constant, and because it's a constant, I'm going to take that outside. 8 into 10 raised to minus 6 divided by 4 into 10 raised to minus 6. Integrate between 2 milliseconds to t dot dt. You plug in the values or the limits of the integration, and you obtain this as your answer. Minus 2t plus 8 into 10 raised to minus 3. Also, the initial stored energy is added on, and that is given by that 4 millivolts. In the olden days, before we had calculators, this is how I used to plot it, how we used to plot it manually. You have the two equations, you plot in the values of t. T equals 0, t equals 0.1, 0.2, 0.3, 0.4. You obtain the values, and you plot it out individually. Now, of course, you can program this in a calculator, online solver, MATLAB, and you can get a direct plot of your expression. T1 was t square. Remember, for the first time period, it was 10 cubed times t square. Second one is linear, 2t. You plot it out, you'll obtain this plot. That's the end of chapter 3. Last slide has a comparison summary of all the equations that you need for chapter 3. Okay. I'll be in my office later on this afternoon. If you have questions, stop by, send me an email, meet me on Zoom. We'll see. I'll bid you a good day, and we'll see you on Friday when we'll begin chapter 4.